Okay, so there are only very brief couple of announcements. One is that this was my mistake, that yesterday I should have told you that there will be there's a high T after the talk, but some of you have left, and those are of course biodegradable substance, so you could not keep it for you for the next day. So you missed that. Some of you got it, but some of you, I'm sorry for that. And today there will be a tea, simple tea and biscuits after this thing. So please join with everyone. So that is one thing. Second is that I request my PhD student Partha Banerjee is also an amateur photographer, and he brought recently a very fancy camera. So he will take a group photograph of all the participants here after the talk. So please be there for that purpose. So we'll all gather in front of the Varti building and we'll take that. So Partho kindly agreed to help me. So with this brief introduction, I invite Professor Simpsoni again for today's talk. So this.
Okay.
And please switch off your mobile.
And please, whenever you ask questions, just wait when the mic is given so that your question is recorded. So please, that's a request. Thank you.
Okay. So let me start. Yesterday, I gave a brief introduction to the quantum Hall effect, and I mentioned the fact that there are various ways to measure the effect in the lab, because eventually what we are doing is measuring current and voltage, and there are different geometries, but they all give the same result. And today I'm going to show you another way of getting the quantized Hall conductance in the integer Hall effect, and that is a geometry of measurement that is using a setup of a Hall bar. So a Hall bar is just, here is our two-dimensional electron system, and we are connecting two contacts here, okay, and I'm using here a coordinate system where this is y direction, this is x. So two contacts are used to channel the current, okay, and there is an ampermeter, and this is the current that we will denote as Ix, and there are two transverse contacts to which you are connecting an electric bias. We call it Vy. Okay, so this is the measurement setup. If you remember from my lecture of yesterday, it was setup B, and it is a little different than what usually experimentalists are measuring, because the more standard way is to use a current source and measure voltage, but you can always exchange it, and this one is more useful to get a very simple derivation of how you get a quantized Hall conductance. So, okay, just okay. So this is the setup, and now to analyze what's going on in the system, let us first understand what we mean by putting a voltage bias. What is a battery doing? Okay, what is a voltage bias doing? It introduces a chemical potential difference between the two sides of the system. Okay, so and that's creating an electric field and creating and generating current if current can pass. So let me write down here. Sorry. It's, there's a delta mu, which is going to be just E times Vy, and that's a difference in the bias, in the Fermi energy, essentially, between the two sides across the system. Okay, so now I also want to put here some geometric factors. So Ly is going to be the width of the system in the y direction, and Lx is the dimension in the x direction. And we are assuming for the moment an ideal system. So there's a free two-dimensional electron gas in this rectangle. And we already solved the problem of its quantum states yesterday. We know how the wave functions look like, and the energy states are just Landau levels. They are quantized harmonic oscillator states. However, one thing that now in this geometry I'm going to care about a lot is the fact that you have boundaries. So when you are deep in the bulk of the system, you can assume that the system is infinite, and the expressions that we got for the wave functions are the same expressions of exact harmonic oscillator states. Okay, I remind you that this is in the bulk. We have wave functions that within the gauge choice that I introduced for the magnetic field, they are going to be free waves in the x direction, but harmonic oscillator states localized near guiding centers yk, where yk is the magnetic length square times k. Okay, these are the states in the bulk. But once you are close to the edge, the wave function cannot be exact, right? Because let's assume now that the system is completely ideal, but at the edge, the wave function must vanish. You have vanishing boundary conditions. And these boundary conditions change the nature of the wave function. And as a result, they also change the energy, okay? So let's see what happens close to an edge. If I'm plotting here the y-axis, in the bulk, we have, let me now look at the state psi 0, okay? So this is just Gaussian, okay? Gaussian wave function in the y direction. And it looks like this. Oh, sorry. Sorry. Yeah. Yeah. So I'm looking at some guiding center that is somewhere in the bulk, where the edges are going to be I'm sorry for that. No, there's no problem. It's just my incompetence in changing the colors in time. Yeah. Okay. So this is going to be the edge, okay? So the wave functions have to vanish here, but in the bulk, the wave function is just a Gaussian of width LB. But when I'm close to the edge, let me just draw the supposed wave function, bulk wave function would be centered around the yk that is very close to the edge. But this is not allowed, it must vanish. So what actually happens is that the wave function is squeezed a little bit, okay? It's squeezed a little bit to allow this boundary condition. Now, when you squeeze a wave function and confine it to a smaller space, what happens to its kinetic energy? It raises up. So as a result, the edge states no longer have just the same energy as all the other states, but their energy is going to rise up, okay? Now, how exactly it rises up, it doesn't matter. But I mean, you can solve it, but the important point is that it rises up. So if now I'm plotting the spectrum, the modified spectrum for a finite system, sorry. Sorry, I want to put it in the middle.
For certain potential, you can actually exactly solve this, right? For a constant electric field.
That's right. There are some potential. For example, if you have, instead of a sharp boundary, you have a quadratic potential.
Quadratic potential and constant.
You can solve it exactly.
Yeah.
That's right.
Okay.
But actually, as I'm going to show you, it doesn't matter what is the potential or whether it's really a sharp edge or a smooth edge. It doesn't matter. It will always give you the same result. Yeah, okay, that's exactly the point. What?
If we take the Born boundary condition instead of hard rules.
Again, it will change the energy, but it will always be. So, what do you mean by?
So we have a boundary condition retreat.
No. So that's okay. That's actually a good question. No. So that now I'm really looking at a finite size system. Okay. So that's important.
Squeezing, right?
Right.
We wouldn't get any squeezing, right?
Right. So if you have a periodic boundary condition, there's no squeezing, and that's actually what we did yesterday. Yesterday, this is exactly the geometry we used. But now I insist of having a finite system.
So that's just compact and non-compact.
Exactly. Right. Now, so it is confined. It's always confined. But how exactly the potential looks, it's not important for us. But qualitatively, the important thing is that the energy is no longer degenerate for all the guiding centers, but it's going to be dispersive. There is going to be some dispersion of the energy as a function of k, or equivalently as a function of yk, which is the guiding center. So now I'm really plotting energy as a function of guiding center, where y changes between Ly over 2 to, okay, these are the edges of the system, okay, and qualitatively, how the energy, how the Landau levels look, they look more or less like this, okay, this is n equal 0, and okay, it doesn't come out very nicely, but this is qualitatively how it looks like. They are still quantized and almost flat in the middle, but near the edge, they rise up, okay? So, so this is how the spectrum now looks. These are the Landau levels, and we're going to now analyze the system. Now let's see, if this is the spectrum, I can now assume in equilibrium that there is some Fermi level somewhere here. Okay. If this is the Fermi level, then all the states below the Fermi level are occupied, and we have equilibrium situation and no current flows because we are at equilibrium. But now I apply a bias, reminding you what does it mean to apply a bias. There's a chemical potential difference, delta mu, and that means that the Fermi energy has a slight bias. It's slightly higher on the right hand side. Let me call it mu r, and on the left side it has a mu l, and there is a delta mu difference between them that is proportional to the voltage. Okay, so all right, so now we're going to get a current going through the system, and we can very easily calculate it. Now, first of all, why do we have a current? Why didn't we have a current when we had an infinite system? If we look at the bulk states, energy as a function of the momentum k is completely flat, okay? Therefore, the group velocity was, let me now write a reminder, is 1 over h bar d epsilon dk, right? It's this is the velocity of propagation along the x direction, because remember k is a momentum in the x direction. So this velocity in the bulk states is 0, right? But near the edge there is some finite velocity, and notice that on the near one edge we have positive velocity, in the other we have negative, right? So and what is this velocity? It's just the local slope of the potential. So so if we linearize the spectrum, here we have one slope that is determined by the local Fermi energy, and on the left you have another slope, okay? And these velocities, if they are not equal to each other, they will give me a net current in one of the directions, okay? But notice once again, the voltage I apply is on the, let me go back to the configuration of the measurement. The voltage is in the transverse direction, but the current will flow in the x direction. Now let's calculate this current, and you'll see that in one line I get the result that we know we expect to get. So I'm computing the total current. What is the total current in the x direction? Just counting the contribution from all the states, and the states are characterized by these k values. So the expression is going to be E over Lx times a sum over all k states of Vk, where Vk is this group velocity. Okay? Let's now go from a sum to an integral and write it as E over, 2 pi integral dk vk. And now there's something important. So the limits of the integral go from the leftmost occupied k state to the uppermost. Actually, let me plot the spectrum again as a function of k, so we'll have it more clearly. It looks something like this, okay? But we have a different chemical potential on each side. This is now I'm plotting it as a function of k, okay? And this is mu r, and mu r corresponds to some k state kr, and this corresponds to some kl, and kr is not minus kl, okay, because there is a difference in bias. Okay, so let us now use the definition of the velocity, and we get the following expression for the current: E over 2 pi h bar integral dk d epsilon dk. Okay? And that's just the integral over k of a one-dimensional, it's a one-dimensional integral, but since I'm integrating over k, what it gives me is nothing but the difference between the energies at the two sides, right? And these energies are exactly these chemical potentials. Okay, so this is in fact delta mu, what I called, and let us plug it in. So first we have a factor of E over h, right? 2 pi h bar is just h. And what is delta mu? It's just E times the voltage. So it's E square, another factor of E, times Vy. Okay? And you see one line, more or less one line, gave us the answer, because the ratio between Ix and Vy is exactly what we call the Hall conductance. Okay, so basically this is it. We get that sigma xy is exactly E square over h. Okay, that's an integer quantum Hall effect, and that's the result coming from one Landau level because of its edge states. If I account, if my Fermi energy is higher and it crosses more than one Landau level, I just get some integer times the same thing, okay? So each Landau level has its own contribution, and pictorially what happens is, if we simplify what this picture suggests, it's the following. So if I'm plotting the sample again, I find that all the electronic states in the interior, in the bulk of the system, are not contributing to current, because it's a flat band with zero group velocity. No current flows there, okay? The current only flows near the edges, and you can basically view it as if there is some current carrying channel, I call it IR, which contributes current that flows to the right, and there's another channel that contributes current flowing to the left. And if you don't have any bias, they cancel each other and you get zero, as you get always in equilibrium. But if you have a bias, you get a net current, and the net current is just IR minus IL, okay? And that's the total, that's the current, okay? Now, not only, yeah, there's a question, yeah?
Yeah, so this assumes that there is no disorder or anything in the bulk.
I'll get to it.
Okay.
I'll get to it in a minute, right? So in the ideal system that I described, the states are really moving in straight lines, right? They are localized along equipotential contours in the y direction, but the current flows straight. And the important thing is that the right moving sector, which comes from one edge, is moving only in one direction, okay? So it's chiral, okay? And on the other edge, we have left movers. And as long as there's no tunneling across the sample because of, I don't know, there's no way to get from here to here, then there is no backscattering. So if you send an electron through the electrode going to the right, it cannot go back. And because there's no backscattering, there's no dissipation and there is no resistance. So it gives you zero resistance, but you can say, oh, but that's not a big deal because I took a perfect system, and now the question is, what happens if I add impurities? What happens if I get impurities? Well,
Besides
yeah,
the top one goes to the right,
yeah,
bottom one goes to the left.
yes.
and vice versa.
Okay, maybe that's a matter of definition of the, yeah, actually you are right that it depends where I define my x direction.
No,
but
but what determines that? What determines that?
The sign of okay, so actually what determines it is the direction of the velocity, okay? So I mean, but you have to define what is the positive direction of x, okay? So the way I defined it, actually the picture is correct because let me go back. If you look, this is so if you look at the energy dispersion as a function of k, okay, the slope is positive, okay, so it goes in the right direction of x. But of course, what happens if I change the sign of the bias Vy? What happens if I change the sign? The direction will not change. What will change is that IR will now become smaller than IL, and the net current will be to the left, okay? So, yeah. Okay? So...
Ma'am, there will be current at the edges. Will there be current in the bulk? Like in the bulk,
so
there
I'm
will
saying,
be group
so
loss
the ideal picture is that in the bulk, or at least within most of the bulk that is up to a magnetic length far from the edge, you get zero velocity in the bulk, no current in the bulk.
So how current flows? Like at the edges, the velocity is non-zero. So how
it
the
flows
current
only,
flows?
the current flows only on the edges. That's exactly the point.
Okay.
The current flows on the edges, but it gives you the current. Yeah, the entire current flows on the edges. At least in principle, it can be carried by one electron on each side. Okay. Okay. So, and the point is, it actually doesn't matter how many electrons participate, because you saw in our calculation, what you see is that eventually you sum over all the contributions.
Yes.
And it's only determined by the energy difference between the two sides, okay? By the way, this is, this is specific to one-dimensional channels, okay? Okay, so this is for the ideal system, but now suppose I introduce impurities, I have rough edges, I have something that spoils the geometry, and maybe I cannot even exactly solve for the wave function. Does the result change? Apparently, and that's quite one of the miraculous things here, it doesn't really matter much, because, so suppose, for example, I have rough edges. So my sample looks like, I don't know, like this, or I have some confining potential that changes a little bit as a function of x. What will happen is, still I'm going to have, my edge channels will now not be straight lines, they will actually follow more or less the equipotential contours of the potential, because altogether, so maybe the flow pattern will be a little more complicated, but it will not change the fact that overall we have more right movers near the one edge and less left movers on the other edge. And as long as the sample is big compared to a magnetic length, which is 100 nanometers, something like that, then there's no tunneling between the edges, and there will be a perfect conductance, okay? So also, even if I'm plotting, if I have some disorder potential, typically the Landau levels will not look like the nice picture I plotted before. They might look like this, okay? This is a function of k, or as a function of yk, which is the same. But and then you can say, oh, but I do have current in the bulk, because I have some right movers here, and here, and here. I have positive slope all over, and I also have some left movers, right? Okay, now what will be my net current? This is some, there's some very complicated function of epsilon as a function of k, but going back to our integral, it doesn't change the result, right? Because the result depends only on the chemical potential difference, that's it. So the current pattern in a typical realistic system, which is always disordered, it will not look like this picture. It will look more like something like this, right? I mean, current flows. There will be some right movers. There will be some left movers, and as long as the disorder is not too big to completely screw up this picture and cause tunneling between the two edges, I will have a quantized current and quantized Hall conductance, okay? Yeah.
The height of the greater than experiment.
Then that's exactly what I mean by too strong. So when the disorder is too strong, then you're right, then it will break down. Actually, also if you have a mesoscopic sample where you have the distance between the two edges is not much larger than magnetic length, or you have a constriction like something like that, okay? There is some some tunneling probability between the edges.
Okay.
That already will spoil a little bit the confinement, okay? But as long as when you have a macroscopic sample, and it's disordered but not too disordered, it will show a quantized conductance. If the disorder is too strong, there is a critical point where you'll have a transition to an insulator. Okay? And in fact, this transition by itself is very interesting because it's going to be a transition from a perfect conductor to an insulator. Okay? So what is the origin? The origin of this lack of dissipation is the chirality. It's the chiral nature of the states because of the strong magnetic field. And that's the essence of the quantum Hall effect. And you see the result for sigma xy is robust to the shape of the sample and to the disorder and so on. Okay, so now what you can conclude from this picture of the edge states is that I don't have to really solve for the wave functions, because these usually do not describe a realistic system. I can think of the state of matter that is called, let us call it a quantum Hall fluid. It is a state where the electrons behave like a perfect fluid. There's no dissipation, but because of confinement and because of the perpendicular magnetic field, there is a chiral motion along the edge. That's basically the phenomenology of the state. So instead of thinking of a Hall bar or some particular geometry, let us take an arbitrary shape of a paddle. It's a paddle of a quantum Hall fluid, which is defined by some confining potential, okay? Let's say some electrostatic potential that in a semiconductor confines the electrons to a region. And quite generally, you can imagine that there is an electric field in any point. It is perpendicular to the edge. So this is an electric field that is minus the gradient of some electrostatic potential, okay? And the velocity, so the system of electrons behaves as if in the bulk nothing happens. The states are localized in some way, or at least they don't have, even if they're not localized, they have zero velocity. But near the edge, because of the confinement, I have some velocity. Okay, and this velocity is chiral. It goes one way. Okay, in some direction, and in principle, if this is a closed loop, it just goes clockwise or counterclockwise, depending on the magnetic field. But that's basically the phenomenology. It's like a fluid that its only degree of freedom is that near the edges you can have some deformation of the density of particles, and they can graze the surface and go around the edges. Okay, so that's what it does, and that always gives you a quantized Hall conductance. So, and let me also do one more small calculation. I want to write now the velocity to actually relate it to this electric field, okay? And that will introduce some more generalized relation between the velocity of electron motion and the confining potential. Okay, so let me write down an expression for this velocity. So initially, it was a group velocity, okay, which is defined as a derivative of energy versus some some k, where k is a quantum number that describes the momentum along the edge. But I remind you that there is this momentum is always related to a guiding center coordinate via multiplication by LB square, where LB is, let me write it down here, LB square is h bar c over E B. It's related to the magnetic field up to universal constants. So instead of writing the group velocity as a derivative of energy with respect to k, I can also write it as in terms of a derivative with respect to y. So let's do it like this. So it's LB square. Okay, sorry. Let me write it more nicely. LB square d epsilon dy. Okay, where here when I say y direction and x direction, I no longer have Cartesian coordinates, but I can define them locally. So at any point, I define this to be a y direction and this to be an x direction. Okay, and it changes. My coordinate system changes slowly with the edge. Why am I writing it like this? Because what is the energy here? The energy is, for a confining potential, it's actually dictated by the potential phi. Okay, so this confining potential is what dictates the dispersion of the energy. And so let me just write it here. So epsilon is actually just electrostatic energy. Okay, that's the energy cost of having the confinement, and therefore its derivative is nothing but the electric field, right? So what I find here is the following expression for velocity, which is, let me use now the expression for the magnetic length. So it's h bar c divided by h bar e b, okay, times there's another factor of e, and minus the phi dy is just the electric field. Okay, so you see that some things here cancel. H bar also cancels, and what I get is that this edge velocity is given by c times e over b, okay, where b is, of course I forgot to mention, b is perpendicular to the paddle, to the surface, and e is in the local y direction, so to speak. If I want to write this equation more nicely as a vector expression, wait, let me write it like this. So the velocity v is velocity of light times, okay, and this is just another way to write it, okay, and maybe you've seen this thing in some context. This is so-called E cross B drift, okay, so when I have a charged fluid, a fluid of charged particles, in a magnetic field and electric field that are perpendicular to each other, I get a velocity which is perpendicular to both. And because the direction of my electric field changes all the time, it's always confining to the edges, I'm going to get a velocity that will, just as this picture suggests, will just go around the paddle, okay? Okay, so that's what the quantum Hall fluid is doing. Now, in that description, you see that, why am I presenting it? Because it suggests that I can forget about the individual electrons, I can forget about wave functions and solving Schrödinger equation. What I have here is a collective description of the problem in terms of fluid dynamics, some kind of hydrodynamics of a chiral fluid, okay? Now, I claim that it's a very useful picture because, of course, when we want to understand the integer effect, we don't need it. We already proved the quantum Hall effect, okay, from first principles. But we know from the experiment that the quantum Hall effect was observed also for fractional fillings of Landau levels. And this is something we cannot explain with a single electron picture, because it's a many-body phenomenon. It comes from from the interactions that allow to form such state, but the phenomenology of this many-body state is the same as for the integer state. So what connects, if we have a collective description, we don't have to care about what the individual particles are doing, okay? So that suggests that we can write a theory for the edge dynamics, which is a field theory, okay? And instead of working with electrons, we work with collective fields that describe them. And these collective fields are going to be density and current, okay? Yeah.
You mentioned that into the surface.
Yeah.
What are the qualifiers for this confining effect with regards to the type of potential V?
It's a gradient of some potential, and it doesn't matter what it is. You see, it doesn't matter because what happens is that you always have whatever potential you have. If you plot equipotential contours, the electrons will follow the equipotential contours. Okay, the gradient is always perpendicular, and the velocity will just follow the equipotential contour.
Yeah, but as such, there is no binding on type of potential you impose on this.
There's no.
You introduce that it has to be confining potential.
Yeah, there is a confining. That's what I assume.
So what is the nature of that function? How this V depends on R? Is there any,
It doesn't. It only depends. It's only, as you see from this expression, it only depends on. It depends only on the gradient of the potential. Okay, that's it. Okay, and it's the same. The important thing is that if you have an equipotential contour, it's actually the same all over the place. Okay, so it's just a constant velocity that is determined by the local confining potential. Okay. Okay, so yeah. Can you repeat the question?
How we can say that the confining potential is equal to the electric field?
No. So the confining potential is this phi. Sorry. This phi. Okay, the electric field is just the gradient of the potential, right?
But when electric field is equal to by some charge, na, but this is the random potential. Na, so in general, we can't say that na, the random potential is equal to electric field, or is its gradient equal to electric field?
No, so okay. So I have a random potential, but what I plotted here is an equipotential contour. Okay, so any random potential. Okay, so maybe I have to make it a little clearer. Because it looks like I jumped ahead a little bit. A general random potential I can plot as some topographic map, right? You know, that's any potential I can plot like this. You have mountains and valleys, and okay, and of course in a macroscopic sample it looks much more. But the wave functions of electrons in a strong magnetic field always follow equipotential contours. Okay, I'm cheating just a little bit because it does assume that the potential changes smoothly on the scale of a magnetic length. Okay, otherwise it's a little more complicated, and you get localization, and it's a little more complicated. Okay,
And
but
one more thing,
that's the picture.
could that but origin of how this potential come into the pictures, no, ma'am?
What if it's a mechanical potential?
What do you mean by mechanical?
There is no electrostatics.
But we are talking about something that affects the electronic system, right? So we are talking about electrons, charged particles, if you like, okay? It's true for any charged particles. But yeah, that's
Thank you.
okay. In fact, just I mean, so yeah. What do you want to say? Yeah.
Actually, we are taught that any potential is a consequence of charge.
Yeah, that's actually also true. But
I had the same thing in mind.
yeah.
Specific charge configuration which you have kept in consideration, leading to some kind of potential that you have involved electric field always.
Look, so actually, always when you have a change, a change of energy, and there is a charged particle responding to the change of energy, you can always convert it to some electrostatic potential via a charge, okay, up to a charge, right? So that's actually, if you look at my derivation. So I started from there is some energy dispersion that has to do with the boundary condition and so on. It doesn't matter where it comes from, you can always convert it into an effective electrostatic potential, okay, for any charged particle, okay? So thank you for the question. Okay, so let me go on. So what I'm hinting here is that I can write a theory that describes the integer quantum Hall effect, just the edge of the edge dynamics, because you see most of the electrons don't participate in transport. You can get all the phenomenology just from the edge states. So I can write a Hamiltonian for the edge states. I can write it for the integer case in terms of electrons. But then I can make a mapping to a collective field and turn this into a hydrodynamical theory. And the hydrodynamical theory can be generalized to the fractional quantum Hall effect. So that's what I want to do. So I start from let's first write the Hamiltonian for the integer. Well, I'll do everything for the integer, but I just write it in a fancy language that looks like, it's like killing a fly with a hammer. I don't know, this is what we say in Hebrew. But this hammer then can be used for killing a bigger animal, okay? So the Hamiltonian for the edge states of the integer quantum Hall state is just a one-dimensional Hamiltonian, okay? It's very simple. Let me write it down. So it's sum over k Okay, so I assume that everybody here knows what I'm writing. These are just the second quantization. I'm writing it in second quantization. CK dagger are electron creation and annihilation operators. And now the epsilon of K is some dispersion that depends on the confining potential and so on. But as we saw, near the Fermi energy, we can always approximate it by a linear form, right? Which just gives me a velocity times k. So let's assume that epsilon k, this is approximately h bar times v times k. Okay, it's linear dispersion. Okay, it's always true near the Fermi level. And therefore the Hamiltonian becomes h bar v sum over k. Okay, so it looks like that, and because it's linear in k,
so you can also do some type of Dirac fermion picture here.
Exactly, that's exactly what I'm going to do. So now I'm switching from k space to real space, and I define the electron field operators psi and psi dagger. Then the linear in k becomes the first derivative, and I get a Dirac Hamiltonian, a one-dimensional Dirac Hamiltonian. But notice that this Dirac Hamiltonian, it's of a chiral. It's a chiral edge state. Okay, it has velocity with a well-defined direction, and this is how it looks in real space. Actually, I have here, let me just check the factors of pi. I don't want to lose. No factor of pi, sorry. Okay, this is a Dirac Hamiltonian. So far what I'm doing is just formulating the one-dimensional single particle picture in a simple way, but here I'm using a field operator to describe the electrons. And the next step that I'm going to do, I'm going to prove to you that the same Hamiltonian can be expressed in terms of a hydrodynamical variable. Okay, how shall we do it? So here is where the big hammer comes, a very fancy trick that is called bosonization. I'm going to introduce a collective field in terms of which I can write the electron operator, and I will replace this description by the collective variable. Okay, so what is it? So let us write, this is a definition, okay? There's actually some prefactor that I'm a bit sloppy about, but let me write it like this, okay? So I represent the fermion operator psi. Psi is an electron operator. It's a fermion operator, and I represent it with an exponential, as an exponential of some field phi.
So first, can I request you to explain a little bit about the context, because there are a lot of students here, they may not be aware of that why directly the fermion Hamiltonian cannot be handled, but you have to go through the bosonization channel. It will be nice if you can tell a little bit about.
Okay, so first of all, this Hamiltonian can be handled without it.
Right.
Okay.
Right.
So what I'm doing now is I'm complicating the problem in order to use it for a more difficult one. Okay, so I didn't have to do it. Okay, the problem is already solved, right? I mean, we have this form. This we know. Okay, we know it's a single particle quadratic Hamiltonian, 3 particles, no need for anything. Okay. So, but now I insist of complicating it, okay? I complicate it by inventing a field phi, in terms of which I can write the electron operator, okay? Now I'm a bit sloppy about, there must be some prefactor to set the units, but let's forget about it because it's a constant, okay? Now, what is this field phi? So we have to remember that we cannot just, I mean, we can write it this way, but we have to make sure that the fermion the electron is a fermion, right? So we know that there must be anti-commutation relations, right? So psi and psi dagger have to obey some anti-commutating relation. I hope this is familiar to everybody, right? So in order for this relation to be enforced, this sets a constraint on the field phi, okay? And I'm not doing any algebra, just telling you the final result. This implies that if I insist of writing the fermion operator like this, phi will have to obey very strange commutation relations. Okay, so phi of x does not commute with phi of x prime, and their commutator is I times pi times a sine function of x minus x prime. Okay? A sine is either plus or minus depending on whether x is bigger or smaller than x prime. So this is a very non-local field. Okay, it's a field that does not commute with itself on any other point in space. Okay.
If you have a circular boundary, how do you think of this? How would you think? What is the sign? If you had like a closed boundary, your x all lie on the boundary, right? Well, how do you think of?
No, but that just
some convention.
It just says that that x equal 0 is identified with x equal L, right? So, if x at the same point, okay. So this is you're asking what is bigger.
What is the ordering here now on circle?
It doesn't matter. You can decide arbitrarily, and everything is consistent. I mean, up to an overall phase, it doesn't matter. Okay.
But
so
we have anti-periodic
why?
For the fermions, you require on the.
No, I mean when you are at the same, when x equals x prime, it's.
No, I'm telling what he's telling you. If we talk about the circle, then it will be periodic or anti-periodic.
No. So again, it's you define it between 0 and L, and you just identify x with L. So when you go back in a circle, it always goes in one direction.
Okay.
Okay. So.
Okay, and k will be quantized in that case, right?
It will, but actually, let us assume, let's forget about that and assume that it's infinite, because the boundary conditions now may be sensitive if you're, but we assume that it's the system is very big, because you see our direction x. Actually, in reality, we want to relate it to this edge of a macroscopic system. Okay. So it just goes around Okay, and yeah.
Perhaps unrelated question. But does this, like all of this quantized connectivity, was it only crucially dependent on the fact that your electron was a fermion? Let's say if I had scalar electrons.
If you had what?
Scalar electron. Would it still work?
Very good question. No, so then you have to define. So you have to. Then you have to. You can also bosonize Majorana fermions, but it will look different. Okay. So now we'll get to it. But for the moment, this psi represents a regular fermion. Okay. And it's a very simple algebra. Actually, it's an exercise to prove that these commutation relations guarantee the left-hand side. Okay, this I give you as the homework. It's very simple. Okay, so good. So and then okay. So now again, I don't have time to do algebra. So just believe me and bear with me. You can show that under this definition, if I write the density operator, which in terms of the original electron fields, it's just psi dagger psi. It has an alternative expression in terms of the field phi, and this expression is this, okay? It's a derivative of phi that gives a local operator that is describing density, just the usual density. And now if I take this Hamiltonian and I rewrite it in terms of the new field, I get the following result. And again, it's the same Hamiltonian. I just plug in the exponential expression for the fields, and I'm getting okay, that's what I'm getting, okay? And I deliberately, again, I avoid the edges and all that, and assume that X is infinite, okay? And it may have some boundary conditions, but that's how the Hamiltonian looks like, okay? Interestingly, so we started from something that is quadratic in the fermionic language, but in terms of the collective density field, it's also quadratic. Okay, it's also simple. Okay, so we did some fancy stuff and replaced one Hamiltonian by another. The new Hamiltonian is also simple, and it is useful for the following reason, because now it's written in terms of a density variable. Okay, now we can just use the Heisenberg relation to get the time derivative of a density. What is the time derivative of a density? This will give me a continuity equation that will be some kind of a wave equation for this fluid, right? And I can very easily get it from this Hamiltonian. Because of the lack of time, well, let me see. Okay, so we'll try to go through it quickly. So, yes? So rho x, yeah, rho x is, yeah, so, I mean, I didn't prove, so there is, here there is, I didn't prove to you this relation, but
I still can't quite see how that's square.
So you cannot see it in a simple, you have to do it carefully. You have to do it carefully. But yeah, but it gives rho, yeah.
A rho square.
Rho square, right? Okay.
So this is how much?
Yeah. Yeah, I mean, this is all in textbooks also. The algebra is not important. I want to stress the concept. Yeah. Giamarchi's book. I mean, if you like, I can give you a list of. And actually, what I'm doing now is also there is some very nice review article by Shagang Wen from '92, I think. Yeah, I mean, the early days of theories of quantum Hall effect, and that's a beautiful review, okay, which does much of what I'm doing here, not in the same order though, not in the same order. Yeah, that one, yeah, that's right, okay. Okay, yeah, and Giamarchi's book has a lot of details, and it's very easy to read. Okay, so let me just quickly show how you proceed with this. So it's more convenient to go again to K-space, and in K-space I can write the Hamiltonian as the sum over K. Let me just see, sorry. I'll write it as an integral. So it's h bar v This is just rewriting the Hamiltonian in K space, where rho K is the Fourier transform of rho of X. And because remember that rho is a derivative of the field phi, so if phi satisfies this algebra, then rho K the operators rho K satisfy the following commutation relations. Okay? That's what you get. Again, it's just algebra to show it in K space. This follows directly from here when you do the Fourier transform. Okay? Now, this is called Kac-Moody algebra. Okay? And it's continuum. Yeah. No edges, forget it. It's X is infinite, K is
sub K, which means it's a discrete K.
Okay, it's just a notation. Okay, but you see, I wrote it as an integral over K, assuming that, yeah. So the quantization of K, I mean, actually, to be careful, you want to think about it as a discrete variable, but you can go to the continuum limit very easily. Okay. So the reason I wrote it like this is because now you see if I look at rho of K and rho of minus K, it appears that they obey a commutator that if I divide by a factor of K, I'm going to get something that looks like a coordinate and momentum, like uncertainty. So I can define a generalized momentum to be pi of K is the conjugate momentum of rho of K, and it's just, let me use just all the factors, it's h bar over I K times rho of minus K. Okay? Okay, so with this, I can easily compute rho K dot, which is the time derivative of rho of k. We know that it's from this quantization of the Hamiltonian, it is just the derivative of h with respect to pi, right? Where pi is this rho minus k. And when you do the algebra again, you're going to get that it's giving me I times v times k rho of minus k. Okay? Very good. Sorry, rho of, sorry, this is rho of k. Yeah. Okay? The same rho of k. You form your Fourier transform back to real space. And what is this equation? It's nothing but the continuity equation, right? So d rho dt is minus dx of j, where j is a current operator, which you can rewrite as, so it's v times rho is a current, okay? So what I wrote here is a continuity equation. And that describes the dynamics of this incompressible fluid, that all it does is you have some deformation of the edge, and that's the thing that propagates, okay? It's a purely hydrodynamical expression, okay? Yeah, there's a question?
Yeah. So how do you prove this is incompressible?
What?
How do you show that this is incompressible fluid?
Well, but because it's a continuity equation, so it describes. So you have a conservation of charge, okay, and so if you go back to your, so basically, what is the intuition behind all this fluid dynamics? If you try to make some density deformation on the edge, it forces it to propagate, but you can only make deformations that maintain the total charge, okay? So to speak. So yeah.
Directly calculate the compressibility from
No, for that, okay. It's a little more subtle than that, but remember, this is just a theory for the edge, okay? So it doesn't give you information about what's in the bulk, but it relies on the fact that the bulk has a quantized relation between current and voltage, okay? That's actually where it's coming from.
Is the coordinate for the future?
Yes, exactly. It's a coordinate that follows the droplet, and you don't care about the shape of it, okay? So it's really a one-dimensional hydrodynamics. And now I want to make another step. So which is going to be a more general interpretation of this Hamiltonian. Notice that the current, so this current operator is a quantized current. We know that it's related to voltage or to potential difference by a quantized sigma xy, okay? So in the bulk, you have the following relation, or actually anywhere, right? We know that this J is also related to some this potential difference on the edges via a quantized sigma xy, okay? So think of delta phi as some kind of a confining potential. That's what creates the current, and this current is related to it by the quantized Hall conductance, okay? sigma xy, and sigma xy is, okay, we know that it is quantized. It's e square over h, because we started from an integer quantum Hall state. And now what I'm doing is I'm going to use these two relations. Notice that we have here two relations. This is one, and this is another one.
Is this phenomenologic? You're just imposing?
No, this. So for the first one, so this one just we just proved it. The second one is not exactly. It follows from our original derivation of the edge mode. Okay, this is how we got it. We got that there is a current, there is a velocity that is related to the E cross B drift. Okay, so it's actually just rewriting this information. Okay, okay, so we see that by using these two expression that relate current to density, one relates. Oh, what did I do? Sorry, save me.
Hello.
So once again, I have my Hamiltonian that is written as a rho square. I have a relation between density and current, and I have a relation between current and the chemical potential difference or confining potential. So what I can do now is to rewrite the Hamiltonian by plugging these relations in the original one, and this gives me the following result. Sorry. So it's going to be okay. And now using the fact that sigma xy is E square over h, it gives me a very simple result. It's just half E square integral of density times electrostatic potential. Okay? So that's one way of interpreting the energy of the edge, or the field theory for the edge. It is nothing but, what is this Hamiltonian describing? Think of it classically, right? It's just electrostatics. You have a droplet of fluid, incompressible charged fluid, and it's confined by some electrostatics, and there is some energy cost to any deformation of the density because of the confining potential. That's what it describes. Okay? So this is in fact universal. Now if you forget that this rho is coming from electrons that are quantum particles and all that, just think of it as a density of a fluid. The same Hamiltonian should be used to describe any fluid, any charged fluid. Okay? So while we derived it for the integer quantum Hall effect, if we want to understand the fractional Hall effect, let us start from it. Okay? Let us start from it. Of course, it will not describe what happens in the bulk. It will just describe the edge theory. Okay? And the edge theory will be of the same nature. And we can, what I wrote now in this purple frame is just electrostatics. So we can use it as a starting point, if you like. But now, what is going to be different for the fractional effect? So So let me just remind you before I get to the.
Is there a length scale in this Hamiltonian?
Yeah, the length scale, it's implicit, but the length scale is the magnetic length, okay? But you don't see it here, right?
But there's no transverse magnetic field. You haven't built it.
No, there is. Where is the, okay, so of course, when I wrote it like this, it's completely universal. It's not even related to a chiral. But if you go back to how this density is related to velocity and to sigma xy, all that information encodes the fact that you have a transverse magnetic field, the fact that you have a Hall effect, and all that is implicit. Okay? Okay?
That's broken from the.
Right. So you see, to get this, I basically used this, and I also used this relation between current and density. With the velocity is the same drift velocity that is also related to the magnetic field in some way. Okay, so that's where it's hidden. Where?
The Hamiltonian on the left, is talking from the left.
This one?
Yeah.
It has, because
The one you.
this one. Okay. So you see this.
One is EK minus EF. Or was that implicit?
It's implicit. Yes, because it is just rewriting the edge state Hamiltonian in second quantization. Yeah.
So you're projecting it on like one Landau level, is it?
Yeah, this is for one Landau level. Yeah. But as I said, adding one more Landau level is trivial. It's just additive. Okay. So let us focus here on just one Landau level. And what I want to do now is to try and generalize it for the fractional effect in the following way. So, and I'm going to focus only on one type of fractions that from the experiment, actually the original experiment that won the Nobel Prize for the fractional quantum Hall effect, what they saw, Tsui, Stormer, and Gossard in their seminal paper, they measured a plateau in rho xy and sigma xy, and exactly the same phenomenology as in the integer, but in a filling factor of 1/3. Okay, that was the first fraction that was observed. Later on, they saw that there's a whole sequence, and today you see a whole zoo of fractional states. But this kind of fractions that are just 1 over some odd integer, they are called Laughlin states. Why Laughlin state? Because Bob Laughlin won a Nobel Prize for guessing the many-body wave function. Okay, he just guessed it, and it was turned out to be right. Okay, it's not a good prescription of how to solve physics problem, but of course there is some intuition behind why he made this educated guess. But that wave function is restrictive to this kind of fractions. You can write wave functions for more complicated fractions, which are variations of it. Okay, so these are. But what I want to stress is that the phenomenology is exactly the same. There is a quantized Hall conductance, there is no dissipation, there's some chiral fluid, incompressible fluid, and the only difference from the integer is the value of sigma xy is not e square over h, but it's e square over h times another number. Okay? So, yeah.
One is the question about Landau. So just in principle, if you were to take into account more Landau levels, you would add just more fermion fields.
Yes.
There would be just multiple number of them.
Yes, with
and they will be
another flavor.
non-interacting, just completely decoupled.
That's right.
Okay.
That's right. And usually it's a great approximation because actually, if you have already, so if your Fermi level passes through one of the higher Landau levels and all the lower ones are occupied, they are behaving trivially because they just contribute an integer background.
Right.
Okay. Right. So
Right. Okay. I also just want to understand this the way that how did you write this? So the Hamiltonian was rho squared integral over dx. And now you are substituting one of the rows in terms of j.
Yes. That's exactly what I did. So let me go back. I take this.
Okay.
And one of the rows, I substitute by j over v. Okay. This is how I cancel the v. Okay. And then I substitute j by delta phi over delta phi times sigma xy.
Okay. So just understand. Are you still going to do like field theory in which you are thinking all of these things as operators which are supposed to act on states?
Yes. So here of course I am allowed to do all these transformations using. I use here quantum fields, but eventually I rewrote it in terms of something that you can also have a classical interpretation.
Right. For example, if you are going to write an expression like j is equal to 0, this is not an operator relation. This is like some probably expectation value in some.
No, but actually,
because the character relation.
Actually, this relation is operator relation. Because j, so if you like, you can also rewrite it in terms of phi, and it gives you a time derivative of phi.
So the relation just above that.
That relation is a field relation because v is constant. Okay. Sigma. So let me check if maybe I had it wrong. Let me check. I may have a mistake.
It's like
sorry. J. Yeah, you're right. Yeah, sorry. In the numerator. Yeah. Thanks for that's
okay.
I just yes, you're right. Actually, let me just that it will not stay here. Let me rewrite it as okay, so it's okay. Now
next day mic 3 लाके different parts में रख दीजिए 3 mics.
Okay. Actually, now I'm a bit confused. So hold on. Let's see. Yeah.
It's phi h bar sigma xy.
Yeah.
That's all.
Okay. Yeah. Okay.
Okay, just to understand the final relation.
Yeah.
Now rho is still like some operator, and this delta y is just whatever potential.
Yeah, that's right. But in fact, the truth is, because sigma xy is also a constant, in fact, this relation is also an operator relation where this delta phi is actually it's more correct to think about it as a self-generated potential, because imagine that you have an incompressible fluid and you make some deformation of the density. Okay, so the Hamiltonian has a self-generated interaction of the density with itself, and the fact that you can relate density to potential it's all going through some fundamental constants. Okay, so the correct thing to think about it is just another way of rewriting the density operator up to constants.
So should I think of delta phi as it's like some functional of rho?
Yes. That's right.
Which I don't know. But do we know it somewhere?
We don't care, okay? We just, what we care is this relation, okay? And this is enforced by the fact that sigma xy is quantized. So if you like, there is the bulk, the quantized Hall conductivity is introduced as a constraint on what happens on the edge, okay?
So in this picture, we are just taking sigma xy to be quantized number?
Exactly. We take it as granted, okay? Somehow we discovered that there is an incompressible fluid, that it has a quantized Hall conductance, and this
gap essentially.
And yeah, that's right. So it, in fact, and that's, by the way, I'm here using implicitly something that is called the bulk edge correspondence. So there's some state in the bulk that is protected by topology, and it imposes some constraints on the edge, okay? That's what, basically, that's a way to look at it, okay? And in fact, this is exactly what Shagang Wen has done. He used it as a, yeah? Okay?
No, they are doing because they have been called for some duty.
Okay, that's fine. But I do have at least 20 minutes or so. Okay, so let me try to get through this part. Sorry. Okay. So what I want to do, I want to use here these two constraints and start from the electrostatic Hamiltonian. And now I want to impose it for the fractional case, where the only thing that changes is the value of sigma xy. Okay? So I'm going to retract my steps to the original Hamiltonian, the way it's written in terms of rho, by starting from this final stage. Okay? Okay, so how am I doing it? I'm repeating the derivation backwards, where the only thing I'm changing is multiplying sigma xy by nu, the filling factor nu, and nu here is different from 1. And the moment, I don't know what it is, it's an arbitrary number different from 1. Okay? And what I'm going to do is the following procedure. I start from this Hamiltonian, and I use these two relations to... What? It will be fractional, yeah. It will be fractional, but at the moment I don't know that it's 1/3, and maybe it's not a rational number, I don't know.
So just
but it's different from 1.
Short peripheral question.
Yeah?
So in spite of everything, this is a picture. So is there a clear experimental evidence of that this deformation and the incompressible fluid picture?
Well, yeah, there are even imaging.
The imaging have been able to see.
Yes, absolutely. Yeah.
Okay.
So a lot of these things were verified and measured. I'll get to actually one of the consequences of it is also okay. We'll just get to it, but I want to explain. So the philosophy is that I'm writing here a collective Hamiltonian, and I want to convert it back to something that depends only on the variable rho of x, where rho x is some kind of a density operator. Okay. So I retract the steps that led to this Hamiltonian, and because of the filling fraction that is not 1, I see that I'm going to get the following Hamiltonian. Again, it's just algebra, a trivial algebra, integral. Okay, and what's the new factor here is that nu appears here in the denominator. Okay. Okay, so let us look at this Hamiltonian, and now it's written in terms of the density. There's only one variable, it's this density of the collective fluid, and on the first sight it looks like it's not a big deal. So what did we change by putting nu not equal to 1? Just a prefactor, okay, constant prefactor. But this constant prefactor is a bit problematic because it appears like the velocity is being normalized. But the velocity is not normalized. The velocity is always given by the E cross B drift. And in fact, what we must find is, if we do again the Heisenberg equation to get the continuity equation from this, it should give us the continuity equation with the same velocity as before. The velocity was not normalized, okay? So we should find that, just retracing our calculation of before, defining momentum and coordinate fields for the density, this thing, dh d pi, okay, this should give us exactly the same continuity equation as before. Sorry, with the same velocity. Okay, this is something that we should get if we correctly quantize the theory. Okay, but then we see that we have a problem. We have here a contradiction, because if we define the momentum operator in exactly the same way as before, just what's written here, this will not work. We have to compensate this factor of nu. Okay, so let's do it. So we keep correcting until we see if we can make a consistent theory out of it. So in order for this to be satisfied, I need to define the momentum operator pi is going to be related to rho minus q minus k again, but with a factor of nu in the denominator. Okay. Okay. This will work fine. But if this is pi, then the algebra of rho k and rho k prime will also change. So it keeps chasing us, and let me rewrite again the Kac-Moody algebra that I'm going to get for the operators rho k prime is going to look similar to before, okay, but with factor nu here, okay? Very good. Okay, what does it mean? Now let's go back to real space, to what we denoted as the field phi, right? Because remember that, just reminding the definition, rho of x was 1 over 2 pi grad phi. So that suggests that also the commutators of phi of x and phi x prime are different. So let's rewrite them. And now you're immediately going to see that we have to be really careful, because it looks, until now, it looks like we allow mu to be anything we want, some arbitrary number. And it doesn't seem to matter, because we can always compensate it. We compensate, but it keeps chasing us into these commutators. And now, okay, now I go back to the beginning. Where did we get this phi from? We bosonized the field, the fermion field psi. But the fermion is a fermion. No way out of it. And if this is still going to give us, so now the question is whether the relation between this phi and the fermion field of the electron is the same as before. The answer is no. Okay, why the answer is no? So let's go back and see what's the problem. So the whole trick about going to the collective variable is I could identify the density operator in the two languages, and the relation is without any factors, okay, except the 1 over 2 pi. Okay, but so there are two problems. First of all, this is going to be violated if I now define my field as before. This will not be satisfied. Okay, so I have to redefine the relation between psi and phi, so that this relation will still hold. Okay, and the way to do it is to write psi as e to the I phi over nu. Okay, I divide it by a factor nu. Okay. Now if you are, now we have to ask ourselves, okay, great. So now everything is consistent, but psi is a fermion, okay? It still has to be a fermion because it's the electron operator. So it must obey the anti-commutator. Let me write them explicitly. If I'm writing psi of x times psi of x prime, if it's a fermion, I must get a minus sign if I interchange them, right? The question is, do I get it? If I start from, so let's just do the algebra. I don't do the algebra, I just tell you what you have to do. Oh, but something is stuck here. Sorry, can you? Okay, so no. Just a bit slow somehow. Okay, now it's good. So you see, I have to. I have this relation, and I want to prove, and I redefine my electron operator in a modified way, and I want to check that this is satisfied. And here it turns out that it cannot work for an arbitrary value of nu, Okay, because for a general nu, if I just I interchange psi of x and psi of x prime using this exponential form. What I'm going to get is a phase factor that depends on the fraction nu in such a way that it's given by e to the I pi over nu psi of x prime psi of x. Okay? That's what I get just explicitly from the algebra of substituting this expression. Okay? Okay, so what is this? So, and now here comes the important point. This cannot be just anything. I no longer have a freedom because I'm back to an electron operator. So this must be minus sign. What is a minus sign? It's e to the I pi times an odd integer. Okay? So for this to be consistent, I must have very particular value of nu. It must be 1 over an odd integer. Okay? All right, so 1/3 is great, 1/5 is great, 1/7. So that already explains, or if you like, give us a hint why all the Laughlin functions or the Laughlin states are like that. And in fact, if we look at most of the fractions where you see the fractional quantum Hall effect, they have an odd integer denominator. There are, of course, there are some even denominator fractional states, but their explanation is, okay, I need another 2-hour lecture for that, but there are more complicated things, but the basic fractions are odd integer, and that's, here we already see it just from an edge theory, okay? So it's again, it doesn't explain the bulk, the nature of the bulk, but it takes it for granted, and but it does give a constraint on what kind of fractional quantum Hall fluids we can get. Okay.
Who is this analysis?
This is Shagan Wen is actually, yeah.
He's the original.
He's the originator. Yeah. Yeah. Ah, so you must know the guy. Yeah. Yeah. No. So he's actually he's really a brilliant, one of the smartest people I ever met. Amazing. Yeah. And you see, I mean, actually, it's really an ingenious theory because the starting point is classical electrostatics. Okay, it's so often what you see now in field theory description of condensed matter phenomena, you can start from some collective theory, and then your constraints eventually tell you something about the quantum particles.
Did you PhD with your God, Edward Wheaton? Yeah.
But just a question. So
Yeah.
if I now rewrite the Hamiltonian back in terms of psi, would it be still a discrete Dirac?
No.
No, it won't be.
No,
Okay, yeah.
that's exactly. In fact, what it will be, okay, it's a Lattinger liquid, a chiral Lattinger liquid. So, okay, so let me just, because I don't have a lot of time, I want to say two things that come out of this, and they are actually can be related to experimentally measurable things. First of all, if I now take the this. Let me now, take this relation, and I want to rewrite it in terms of this integer m. So psi of x is e to the I m phi, right? So you can think of it as a field that has the original form e to the I phi, and just take a product of it m times, right? So let me define an operator of a quasi-particle, which I define as e to the I phi, okay? What is this particle? It's not a fermion, okay, for the reason we said, but we can see that because m is an integer, I can actually write psi as a product of m times psi q, okay? So we can think of the electron operator as something that is composed from m quasi-particles, okay? So
this can be directly called anionic creation operator or anything like that?
Yeah, so you're jumping a bit ahead. So first of all, I can view the electron as something that is composed of fractional objects, okay? And the creation operator of an electron is creating m quasi-particles. And these quasi-particles are not fermions. They have fractional statistics, and how do you see it? Just like what we saw before, that if you take the psi q of x and psi q of x prime, and you interchange them, you don't get a minus sign. What you get is it's you just get just I pi nu psi q x prime psi q of x, okay? And this phase is a fractional phase, okay? So they have a fractional statistics. For the 1/3, it's going to be pi over 3. And this is an anion, okay? So first of all, they're going to have a fractional statistics. They also have fractional charge, because one electron is actually 3 or m quasi-particles in general. So they have fractional statistics, and they also have they have a charge E, which is actually E times nu, which is E over m in general, okay? They're like quarks in a sense, okay? Now, actually, these are going to be the elementary excitations of the system. So if we go back of thinking, what is the nature of the quantum fluid, the fractional quantum Hall fluid? It's an incompressible state which comes from some many-body function. The many-body function is generated by interaction, because if we're talking about states in the lowest Landau level, remember the Landau level is flat. There's no, and let's assume now there's no potential, it's clean, no disorder. It's just a flat band. So the only thing that can contribute to energy is interaction. Electron-electron interaction is everything, okay? And that also dictates how much energy it costs to create an elementary excitation. Now, if that's the only energy cost, and it suggests that the elementary particle here, or the elementary excitation of the state, is not the electron. It's going to be something that has a smaller charge, because the energy scale for let me call it, if we're looking at the energy gap for excitations, okay, energy gap is going to be up to some numerical factor, is going to be just a Coulomb energy. A Coulomb energy in the quantum Hall fluid, there's only one length scale, that's the magnetic length. So it's going to be some charge squared over L. Now, since E star is smaller than E, it's cheaper to create a quasi-particle, so that will be the elementary excitation, okay? So the prediction is, and yeah, that's right, it's an activation gap that costs, to get out to basically to overcome the gap to the
What are the typical values?
So it's pretty big, but okay, I think it's millikelvins. No, sorry, it's okay. So it's so when you go below Kelvin, you are below the gap. So it's you have to. So in order to see the fractional quantum Hall effect, you have to go to sub-Kelvin regime. Yeah, so it's a further Kelvin actually, or maybe 0.1 Kelvin. Okay, but the point I want to make is that there is a prediction just from all these simple consideration that there will be an elementary particle, elementary excitation that has a fractional charge and fractional statistics. And that's an experimental prediction, because you can do something like a shot noise experiment in a constriction. And that experiment, in fact, was done by someone from the Technion, Misha Reznikov, long time ago. It was proven that you get fractionally charged quasi-particles. There were attempts to show that it has fractional statistics, but that's much more difficult to show. You need some interference experiments, but that's much harder. But that's the prediction, and that was also the prediction of Laughlin from his wave function, just mathematical prediction. But here you see it also comes naturally from the edge theory, okay? So that's a highly non-trivial result of a many-body state that has anomalous kind of quasi-particles, anionic. And another result is, you were asking about the Hamiltonian, how it will look like in terms of some other fermionic field theory. So of course it will not be a free fermion, but if you are, so I don't have time to go through the mathematics, but if you rewrite this phi, this field that I called phi, if you write it in terms of non-chiral fields, and you just look at the right and left movers as one entity that has right movers plus left movers, and you write a field theory for the entire thing, you get exactly the form of a Lattinger liquid, which is in usual 1D electrons, it comes from a model where you take Dirac electrons plus interaction. and it has a Latinger parameter. So anybody's, I don't have time to get into this, but if you take electrons with interaction in 1D, and the kinetic part, the free part of the electron is a Dirac, it's linear dispersion, you can see that in bosonization you can map it to a free oscillator theory again, and that's called the Latinger liquid, and it has a Latinger parameter that we denote as K, and in the usual Latinger liquid, it's given by something that depends on the interactions, okay? This is something that I mentioned before, Giamarchi's book. You can read about it. So there's some parameter that encodes interactions, and this parameter becomes 1 when the interactions are 0, okay? Now, in our case, we get something that formally is the Hamiltonian of a Latinger liquid, but where K is not related to interactions. It's related to the filling factor, okay? So this H, this Hamiltonian that we get, can be mapped to a Latinger liquid with where K is the inverse of nu. So it's a very strange thing. So it looks like something that is coming from interactions, but the parameter that appears there is actually related to the bulk state, okay? It's this quantized Hall conductance. So that's another way in which there is a correspondence between bulk and edge. So the edge behaves like something that has something that looks like a parameter, interaction parameter, but this parameter is nothing but sigma xy of the bulk. Okay? And one of the predictions of it is that if you measure do a tunneling experiment into a quantum Hall fluid, the IV characteristic will have a nonlinear power law, and this power law is exactly related to this Latinger parameter. So that's another experimental prediction that comes from, that is this coming from this theory actually, okay? And you see it in experiments, although there is a question about the interpretation of the power law that you actually get, but in principle it should be just that, okay? So I think here I'll have to stop and just let you, yeah. So I guess this was a bit condensed. If you want to understand some more details, please come to me and I'll be happy to answer questions.